Okay, our next problem involves folding a piece of paper. I'll just kind of actually show you what this is all about. So if I take a piece of paper and I'll fold this corner up here, I'll fold that corner down so that it touches the bottom of the page. All right, fold that paper so top corner, fold it down so it touches the bottom of the page, and you can see that there is there's a triangle down here in the corner that's formed. And that's what this larger diagram is all about here. And okay, so ultimately there's a big question here, which is the big question is how would I fold this paper down to maximize the area of this triangle right here? So just take a look again. I could, for example, fold the paper down so that it touched right there in the corner, and there's no triangle at all, no area. Or I could fold it over here somewhere, right? Or I could fold it maybe, so this triangle is like this. Right, so if the triangle is very wide, but it's short, or I could fold it so that it is. I'll draw another one here. Okay. Right, it looks like it's kind of taller and skinnier. Or I suppose I could fold it all the way over so that the paper is completely flat, and again, there's no triangle at all, so no area. But somewhere in the middle there, somewhere, we should be able to find a place where the triangle, outline it there, it's a little hard to see, is the largest possible. Well, before that, we have to figure out how we're going to calculate the triangle's area at all before we can figure that out. So let's start with that. So here in this triangle, in this particular paper, and I've drawn this on the grid so that the height of the paper is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. 9 spaces tall. And the width of the paper is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. Okay, and these are just spaces on this grid. So I could actually cut this little rectangle out, and that would actually be my sheet of paper. And we're going to say that the distance from D to E, we're going to call that X. Okay, so that's going to be our input variable. But basically, it's where I choose to fold the paper right here. Of course, not everything is a possibility for X, if you think about it. The highest up I could possibly fold this sheet of paper would be 4.5 spaces. I'll show you why. If I double paper this on this side. If I fold it 4.5 spaces, that's exactly over and a half, and the corner touches right down here. Any higher up than that, and it won't reach the corner at all. So 4.5 is the minimum. And of course, the maximum that I could fold it down would be if I folded it, if I made the fold all the way down here at C, and that would be as if we're actually folding the paper into kind of almost like a triangle shape. Right, that's the other point where there's no triangle at all down at the bottom. So the maximum I could make X is all 9 spaces. So let's just make a note of that. That 4.5 and 9 are kind of lower and upper bound for where X can be. I can't make the fold shorter, the fold distance shorter than 4.5. I can't make it bigger than 9. All right, so next of all, to find the area of this triangle, I'm going to have to know what this distance is right here and what this distance is right here. Well, this distance here, that's going to be fairly easy. It's just whatever's left over after the fold out of the whole 9 inches. Now this distance down here, we're going to have to use some Pythagorean theorem, because of course that is a right triangle. And we're going to go c squared minus a squared equals b squared. So let's see here. First of all, we have our DE. I'm just going to make a little kind of a little table here. That's going to be our input variable x. And then we need to know EC. And that's going to be, we're going to calculate that as 9 minus x. And then EF, that's going to be the same as x, right? That's just, this is just the edge of the paper that's folded over. And then FC, now that's where it gets a little bit complicated. It's c squared minus b squared equals a squared. Let's take a look at how I get that. We've got a squared plus b squared equals c squared. That's our Pythagorean theorem, but we already know c. So I'm going to choose one of these legs to be the bottom. And then we're just going to subtract a from each side. Okay. So b squared is c squared minus a squared. If I actually solve for b, I get the square root of c squared minus a squared. But remember, in here, c squared, or c, is just our variable, input variable x. And the, if I call this c, and this a, and that b, c is just our input variable x. It's the same as the same part of the paper I peeled off in the first place. A is just what's left over after I take this x out of 9, so it's 9 minus x. And then b down here is the one that we're solving for. So this ends up being FC is the square root of x squared minus, this is a, where I determined that a is, or EC, is 9 minus x. So that is 9 minus x squared, all inside the square root bracket. So in the area of triangle EFC, okay, the formula for area is area equals base times height divided by 2. And the base of this triangle is FC, this formula here, and that is, let's see, square root of x squared minus 9 minus x squared, okay, that whole mess times the height, that's a right here, which is just the 9 minus x, and divide that by 2. That's kind of an ugly looking formula. Well, let's test it out for this particular case. I chose these dimensions of the paper very specifically so that when I folded it down, I would end up with this 3, 4, 5 right triangle. So you see x is 1, 2, 3, 4, 5, and a is 1, 2, 3, 4, and b down here, the base, is 1, 2, 3. So the area of this triangle, this particular triangle, is simply 1, 2, 3, 4 times 3 is 12 divided by 2 is 6. So let's check to see if our formula works out that way. Alright, so A equals, so let's see, put in my big formula here. Our input x in this particular case is 5. So let's see. We have 5 squared minus 9 minus 5 squared. And over here I have 9 minus 5. And all of that over 2. Let's see. 5 squared is 25. 9 minus 5 is 4, and 4 squared is 16. Okay, I'm just working this a little bit at a time here. Oh, I'm off the page there. So 5 squared is 25. 9 minus 5 is 4. 4 squared is 16. So I'm just doing a little bit at a time. 25 minus 16 is 9, and the square root of 9 is 3. 9 minus 5 is 4. all that over 2, and kind of see where things are headed now. 3 times 4 is 12. 12 divided by 2 is 6, just like we observed. So our formula works for this particular case. Okay. So again, let's just review what we've done. We've talked about this diagram. We're folding this paper down and to make this little right triangle in the corner. The hypotenuse of this right triangle, the c and a squared plus b squared equals c squared, is simply the same as the amount that we're folded down by, and that was what we chose to be our input variable. The height of the triangle, which is the a, and a squared plus b squared equals c squared, is just what's left over after we remove the x from the top. In this case, since this the whole piece of paper is 9 units tall, then this EC part is just going to be 9 minus x. EF, the part that's folded over till it touches the corner, is the same as the amount that we called x, the top of the paper that's been folded down. That's what that is, the same piece of paper. So that's also just x. EF is just x. And then finally, B, that was a little complicated one, ended up being x squared minus 9 minus x squared, and we take the whole square root of that. This whole business in here really could be simplified, but I just wanted to leave it that way so that we could kind of see where everything came from, because this comes from the square root of c squared minus b squared, which is our kind of our reworked Pythagorean theorem. B squared, or not, I'm sorry, this is a squared in our diagram. All right, c squared minus a squared, where a came from here and c came from here. We're solving for b, and that was side FC. I'll write that down here a little bit clearer. That's c squared minus a squared. Okay. Then we tested it out to find the area of this particular triangle right here, and we got 6 units squared, which is what we anticipated. So the big question then, and this is the more complicated one, is when is this triangle right here its maximum possible area? And we'll look into that in a separate video.